Alright, let's sketch the following graph. F of x is equal to 1 over x if x is less than 1, and negative x if x is greater or equal to 1. So this basically is a piecewise function. So a piecewise function is a function that contains two or more functions that occur at different intervals, right? So we notice that the function is going to look like 1 over x if x is less than 1, and the function will look like negative x if x is greater or equal to 1. So when x is less than 1, we'll have a reciprocal function. If x is greater or equal to 1, we'll have a linear function. Okay, so we know that f of 1 cannot be a reciprocal function because this is actually excluding the 1 itself. So f of 1 should not equal 1 over 1. Okay, so that means that f of 1 should not equal 1. So the point 1 and 1 doesn't exist. Okay, so if the point 1 and 1 doesn't exist, then that tells us that there is a discontinuity at this point. Okay, so there's discontinuity at this point, and or we can think about this as a whole, right? So it's discontinuous at x is equal to 1 at this function, but we also know that f of 1 can fit into the equation negative x, so it'll look like when we plug in 1 for x, we get negative 1. So 1 and negative 1 will exist, right? So 1 and negative 1 will exist, so we basically have a point here, okay? Now as long as x is greater or equal to 1, we can use this function. So f of 2 here will look like negative, I'm going to plug in, it's going to look like negative x, so I'm going to plug in 2 for x and you get negative 2, right? So 2 and negative 2 is a function, right? So 2 and negative 2 will look like that, right? And so forth. Like f of 3 here is basically negative, and you plug in 3 into the equation, you get negative 3. And so we'll just kind of keep going like that and so forth, right? So you can see that there's a linear function that's being created down here, and it's going to keep going straight down, right? Now, as x is less than 1, right, we can also assess that in the domain of this function, 1 over x, right, x belongs to a set of all real numbers, but x cannot equal 0, right? So there's a restriction on x, so we have to be careful with that. We can make it get smaller and smaller to 0, but it won't touch 0. So when you have a restriction, this is actually implies there's a vertical asymptote. So there's a vertical asymptote when x approaches 0, and I'm going to show you that vertical asymptote by highlighting that the y-axis here is a vertical asymptote. Okay, so this whole y-axis is the vertical asymptote, right, when x is equal to 0, and because of that the graph actually won't hit that point, so it'll get closer and closer to that point, but it'll never touch, right? Like for instance, if we plug in f of 1/2, which is less than 1, it's going to give us 1 over 1/2 for x, and we're going to get 2, right? So we're going to get 1/2, which is here, and 2, so it's going to keep getting smaller and smaller, right, until we get to a point that is closer and closer to 0, but as it does that, the function actually will approach infinity. Okay, so the function will approach positive infinity, right? So as x approaches 0, y is going to be approaching positive infinity. Okay, so that's the idea, or you can kind of think about this using limits if you have considered a calculus course, right? But for the time being, we'll kind of not address this using limits. Okay, so that's what the function will look like there, but we can understand that x can be equal to negative 1/2, right? Which is going to give us 1 over negative 1/2, which is negative 2. So in this case, negative 1/2 is going to give us negative 2, and you can notice here that you can also approach the vertical asymptote from the left side, right? So f of negative 1 here is equal to negative 1, right? So it's 1 over negative 1, which is negative 1, right? So you notice here that you can also approach the vertical asymptote from this side as well. So, right, I'm just going to start with that. Right, so it's going to keep going like that. And we can kind of understand how this would work, right? Okay, so the graph will kind of look like this. Now, we can also notice here that the range of this reciprocal function is y belongs to all real numbers, but y cannot equal 0. And the reason y cannot equal 0 is because of the fact that there is no way to make this fraction equal 0, right? You can only make a fraction equal 0 when the numerator is equal to 0. So because the numerator isn't equal to 0, y can't equal 0. The restriction on the range here is what we call the horizontal asymptote. So there's a horizontal asymptote at y is equal to 0. I'm going to highlight the horizontal asymptote. I'm going to use green to represent that. So there is a horizontal asymptote when the graph approaches x, right? And in this sense, y can never approach 0. So you can see that the graph actually will approach 0 as x approaches negative infinity. So as x approaches negative infinity, y will get closer and closer to 0, right? Also, we can understand that if you approach the vertical asymptote from the left side, right, x approaches the asymptote from the left side. I'm going to use the right side and the left side of the vertical asymptote using plus and negative. So we stated that as x approached the vertical asymptote 0 from the right side, y was going to approach positive infinity. You can see that the trace in red is going all the way to positive infinity. But if I approach x is going this way to 0, you can see that y is approaching negative infinity, right? So y approaches negative infinity. So this is just really useful to understand some of the end behaviors of this function. And we can notice here that the restrictions of one portion of the piecewise function can be applied for the whole thing. We know that if we look at the second portion of the piecewise function, the negative x, well, if you look at negative x, the domain here, x belongs to all real numbers, and y belongs to all real numbers, as long as x is greater or equal to 1, right? So we want to kind of include that, but x has to be greater or equal to 1, right? But here we have our restriction for our reciprocal, but we also here we have an interval for a reciprocal, but we also have a restriction for a reciprocal. So we have to be very careful when looking at the domain and range of the function, right? So it's very important to understand each of the individual domains and ranges of the functions that make up the piecewise function. Okay, so create a piecewise function for each scenario, or the following function is continuous. Explain for part A. We can notice here that we have two intervals. One of the intervals here is x is, whoops, sorry about that. X is less than or equal to 1. The other interval is x is greater than 1. So for the interval where x is less than or equal to 1, it looks like a quadratic function, right? And you can tell by just kind of plugging some points in. So you'll get 0, negative 2, you'll get the point negative 2 and negative 2 and 2. Okay, so a quick way to kind of do this is if you have 0, negative 2, we can basically do x squared minus 2. That would work, right? And if you test out negative 2, you'll also get f of negative 2 here should give you negative 2 squared minus 2, which is 4 minus 2, which is 2. Okay, so you'd have to create a function that would involve all of the points on that graph shown. So x squared minus 2 would work for x is less than or equal to 1, right? So f of 1 should look like 1 squared minus 2, which is negative 1. So we actually have that point, 1 and negative 1, right? But f of 1 here should not equal 2. Okay, so 1 should not equal 2. So you can already tell that because we have a break, and there's the break here, because we have a break in this function, this is not continuous. I still need to create an equation for the other function. Now you can notice here that at 2 we have 3, at 3 we have 4, at 4 we have 5. Right, so it looks like it's 1 higher than, the y value is 1 higher than the x value, so I'm just going to do x plus 1 here. Okay, so this is not a continuous function, guys. Right, I'm going to call this f of x. Right, and this is basically what our equation will look like. Let's take a look at the next example. So in example B, we can notice here that we have two intervals. So we have the interval x is less than or equal to 1, right? And this basically will look like a piecewise function because it has the signature V shape. right? So it's very important to understand some of the parent functions and what their behaviors look like. The other value here, x is greater than 1, right? Now you could also switch it up. You can make it x is less than 1, x is greater or equal to 1. I'll give you the same result. But you can notice here that the hole that was once here, that was present, is basically being filled by the other equation. So for x is less than or equal to 1, I'm going to make the function resemble an absolute value function. So it's the absolute value of x, because it has the points, this is -1 and 1, this is -2 and 2. Right, so it mimics an absolute value function. Beyond x is greater than 1, I'm going to make it a square root function, so I'm going to call it square root x. You can notice here that f of 1 here should be equal to an absolute value of 1. So 1 and 1 exists, but f of 1 should not be equal to the square root of 1, which is equal to 1. So 1 of 1 doesn't exist. So because the point that doesn't exist is filled by the point that does exist, then this is continuous. Okay, so this is continuous as a result. So if you have the same value of y for each of the n values of the interval, then the point will be continuous. So this function therefore is continuous. And this is the equation of that piecewise function. Okay, find the value of k that makes the following function continuous. Graph the function. Okay, so we have two different functions here. One function x squared minus k exists where x is less than -1. The other function 2x minus 1 exists where x is greater or equal to -1. If I want to make it continuous at all points, I need to look at this interval. So if I'm looking at this interval, I need to look at the n value of each interval, right? So f of -1 should not equal -1 squared minus k, because this interval up top here should only exist where x is less than -1, so it doesn't equal -1. So f of -1 should not equal 1 minus k, right? But f of -1 here can equal the second function here, 2x minus 1, 2 times -1 minus 1, which is -3. So f of -1 can equal -3. Now, by itself, there's going to be a hole at this point. So there's basically a hole or a point discontinuity. Well, I should put hole as in quotation marks. There's a point discontinuity that occurs at -1 and 1 minus k, right? So because there's a point discontinuity, the function would be discontinuous. If we equate this value with the -3, then the function will be continuous again. So I'm going to let 1 minus k equal -3. If I move the 1 to the other side, -k is -3 minus 1. -k is equal to -4. If I want to solve for k, I'm going to divide by -1 to both sides. K here is equal to 4. So if k is equal to 4, then the piecewise function f of x will look like x squared minus 4 and 2x minus 1. X is less than -1 and x is greater or equal to -1. You can notice here that at f of -1 here, it shouldn't equal -1 squared minus 4, which is -3. But f of -1 here can equal 2 times -1 minus 1, which is -3. And the hole, which is this value, is basically being filled by the other value of the function. Okay, so that's where all points will become continuous. So let's take a look at a question regarding piecewise functions. If f of x is equal to x squared plus 1, if x is less than 1, and 3x if x is greater or equal to 1, is f of x continuous at x is equal to 1? And explain. Okay, so what we need to do here is, in order for us to determine if f of x is continuous at x is equal to 1, whatever hole gets generated at x is equal to 1 should be filled by the other function in the piecewise function. So let's test to see if there are any point discontinuities, and there should be a point discontinuity because one of the functions is not present when x is equal to 1, and this is specifically x squared plus 1, right? The function x squared plus 1 only exists when x is less than 1. So therefore, f of 1 should not equal 1 being plugged into this equation. So 1 squared plus 1, which is equal to 2. So the point 1 and 2 does not exist, right? So this point would not exist on the graph, right? but f of 1 should be found in the function 3 of x. So if you do plug in x is equal to 1, it should be plugged into 1 for 3, and then you get 3 times 1, which is 3. So the point 1 and 3 does exist, right? So this guy exists, right? So in this case, because we do have a hole at 1 and 2, and the point exists at 1 and 3, right? This would not be continuous at x equal 1. So I'm going to show you guys this graphically. All right, so let's graph this function on this graph, right? So let's first graph x squared plus 1 on this graph. X squared plus 1 looks like a quadratic function. So we know that the point 1 and 2 doesn't exist, right? Because in this case, the condition for this function is x has to be less than 1. So 1 and 2 will actually just kind of look like a hole, right? Whoops, let's just kind of move that there. So it's going to be a hole at this point. However, 1 and 3 should exist, right? So 1 and 3 should exist. Now, as x is greater than 1, the function should look like 3x. So if I do f of 2, then the function here would be 3 times 2, which is 6, right? So you would get 2 and 6. Let's put that here, right? And just be a linear function, right? So just kind of keep going, right, further on. Right, now in this case, let's take a look at x is less than 1. Well, if x is less than 1, let's do f of 0. F of 0 here is 0 squared plus 1. We plug it into this equation, and we get 1, right? So 0 and 1 will exist, right? And this should be concave up, right? And if we do f of negative 1, we get negative 1 squared plus 1, which is 2, right? So you can kind of understand how this would work. So this would be basically a quadratic. Right, and you can notice here that at this point we have a discontinuity, and a discontinuity is a break in the function. So this is the break or the discontinuity. Okay, and if you guys take future courses, specifically calculus, this is a type of discontinuity, and it's called a jump discontinuity. Okay, so it's not too important for us to understand, but there is a discontinuity in this piecewise function that's signaled by this break. Right, so therefore f of x is not continuous at x is equal to 1.